Alright, so let's try this example here. What is the integral of ln x over x and dx? Now, that looks complex, isn't it? But watch this, how we use the method of u substitution into this particular problem. So, the goal here being is for us to be able to properly use the u substitution into the right way. So I'll give you a perfect example. Say if we are going to use the u substitution into the wrong place, say 1 over x, and the u will be minus 1 over x squared. So, and the sole purpose of this really is to plug it back into this equation here, just to simplify it even further. But in this case, even though we can substitute u, but what about for du? Can we really put du back in our equation here? Of course we can't. So in this case, we have to pick the right way of our substitution. But what about if we use ln x? Let's go try this one out. Oh, sorry. I meant to say, you know what? I'll put back the right color. That's the wrong one. See this one? There you go. It's getting better now. Okay. But what about if we use ln x instead of 1 over x as our u substitution? What will we get? Okay, it's right here. So it's going to be ln x. And note that the derivative of ln x is 1 over x and dx. Okay, in this case, we can not only substitute our u here, which is ln x, but also we are able to substitute du into x and dx. In this case, we have u du, and really is the integral of u is just u squared over 2 plus the c constant, and we just have to substitute our u, which is ln x squared over 2 plus c, and right here is our final solutions to our problem. Now here we've got a nice and smooth question of x plus 5 all the way to the power of 6 dx, and we are asked what is the integral of this function. Okay, well, one thing's for sure is that if we are going to take our u as x plus 5 and really differentiating it will yield it 1 times dx. Now, we're ready. We are so ready that we are gonna just plug in the values back to its original equation. And I'm gonna put a label here just so you guys can understand where it goes to what. So remember, this entire thing here is our u now. Differentiating it will change this into du. In this case, we're gonna have the integral of u to the power of 6 and du. Okay, integrating this will gives us u to the power of 7 over 7 plus c, and plugging in our u back will gives us, and we use green this time, will gives us x plus 5 to the power of 7 over 7 plus our big constant c. And note that, again, c is a constant and can be any value. So pretty much what this means is that our solution can have various answers. It can be x plus 5 to the power of 7 over 7 plus 1, or x plus 5 to the power of 7 over 7 plus a million, or x plus 5 to the power of 7 over 7 minus 1 trillion, whatever that is. C can be any number. Now, if we have I'm going to use this question for further explanations. If we are given this point here, say 1, 2, 1, this is x and this is y, and using this point, we are able to plug this entire thing back here to our equation to figure out our c constant. In this case, we have here 1 plus 1 plus 5 power 7 plus c. And by the way, this is supposed to be equal sign, not plus sign. My bad. Now that's 6 times, hold on. So let's see here. So we've got 1 equals to 1 plus 5 to the power of 7 minus 7, and it's gonna be subtracted by 1. I think we've got about, hold on, let me just clear everything out. I think we've got about, our c will be around approximately, let me double check again. Around 3,990.85. I think that might be the approximate value. The thing is, if we are given some particular coordinates of x and y, we should be able to figure out our constant c. Alright, so we have this solution here, or this question, sorry. And we are going to integrate this by using the u substitution. In this case, we can let 1 plus 2x as our u here. So in that case, our u is equals to 1 plus 2x. So differentiating u will lead us to dx. Note that we don't really have 2 in here in this equation. We only have dx. So the question arises, where does this 2 is gonna go now? Because remember, there's no 2 around here. We only have dx. So however, if we are going to divide this dx over by 2, which will gives us dx, we should be able to substitute dx over here. Now let's proceed our further integration, which gives us the square root of u times du over 2. Now this is actually a constant and does not affect in any integration practices. So this is going to be moving out here, outside the integral, which will gives us 2 to the integral of the square root of u du. And the square root of du, which is, by the way, u is equal to 1 over 2 plus 1 over 1/2 plus 1 plus c times 2, which gives us, and by the way, this is gonna be a 2 here, so it will gives us 4 times u to the power of 3/2 plus c. And our u here, remember, is 1 plus 2x which in that case we're gonna have 4 times 1 plus 2x to the power of 3 halves plus c. And right here is our solution. With 2 butterflies. Alright, hey guys, so I have this question here of the integral of x times e to the power of x squared over all times dx. Now, note that our u here is x squared. It is an x squared right here. And that our du here is the dx and the x here. So if we chose x squared as our u, we have to differentiate it back to get 2x with dx2. And yeah, here we are. We just plug every values in here, which leaves us into 1/2 times e to the power of u times du. And the solution for that will gives us, it will gives us 1/2 times e to the u plus the constant c. And by the way, it doesn't matter what the integral of e to the x or what is the derivative of e to the x, it's still going to be the same. And our u here is x squared, so that's gonna be e to the power of x squared plus c. This right here is our integral. Now, if you're uncertain about this answer, by the way, if you are going to differentiate this function, so if you are going to differentiate this function here, this should be able to revert back into its original position. So let's test that hypothesis. So what is the derivative of 1/2 times e to the x squared plus c? Okay, note that we have to use our u substitution squared, so it's going to be 1/2 e to the u plus c, and that's going to give us to dx. Remember that in a differential calculus, there's this thing called chain rule. Now the chain rule states that this overall function here are differentiated, or dy over dx is differentiated by du over dx, which in this case our du over dx is actually this one times the overall derivative of the function, which is, well, du over dx, this overall thing here. Sorry, I mean dy over du, my bad. Dy over du, which makes sense because if we are going to cancel this one out, this will become dy over dx. Now, so since we have found our du over dx, let's differentiate this. And by the way, it gives us e to the u, that's 1/2, times 2x. And note that we also have to substitute our u here, which will gives us x squared, and this will cancel out, which will gives us x times e to the power of x squared. Okay, let's go ahead and zoom everything out so you can see everything. Now remember back then that we have differentiated this, that we have integrated this function. Integrate. Which gives us 1/2 times e to the power of x squared plus c. And if that's going to be differentiated, it will revert back into its original state, which we just note that this original function, if it's integrated, it gives us this value. But if we are going to differentiate this function here, this will go back into this original function. So in this case here, this here is equal to this. Okay, I think my cat just scratched my drawing, so I do apologize about the quality of my overall picture right now. But the point here is that by solving the u substitution, we have to make sure that we are using the right value as a u substitution. And just by really differentiate that u into du and plugging everything back into its original position, and by the way, by all means of simplification, algebraic manipulation, and integrals, we should be able to get our solution. So it's all about trial and error. Okay, thank you guys for watching, and be sure to subscribe to my channel for more content, and I will see you all in the next video. Peace.